Hi there everyone, in this tutorial I'm going to take you through the 2020 Unified Chemistry exam, which is paper 3 on the OCR A-level in chemistry. In this video I'm going to use various different ink colours and highlights to emphasise how I would answer the questions, but please make sure you only use black ink on the day of your exam. The first question here is about organic chemistry and we're being asked to label up a reflux apparatus. Here, the only thing I can imagine you would get massively wrong is maybe the direction of flow of the water, but that's an easy fix to help you make good progress with the outcome from this paper. And don't forget, you can describe this at the bottom here as either a pear-shaped flask, which is the one being used here, or you could actually describe or draw it as a round bottom flask. Make sure, just again to remind you, that you can draw a reflux and a distillation ready for your exam. We've also got for the next part of this, the demand of actually drawing our own diagram for filtration under reduced pressure, which is for part of the apparatus we would use in purification of organic solids in a recrystallization. Now, if I just zoom in on this, unfortunately the mark scheme didn't actually carry with it an example of what this diagram should look like, but the diagram I've got here includes all of the points that they wanted you to have in order to secure the marks for this question. The kinds of things they wanted you to include were a Buchner funnel and a Buchner flask, that there's a tight seal for how the flask connects to the funnel, and that you've got a single side arm here connected to a vacuum. Moving on, and this next question is all about amines, and we've got 3 different amines here which are all structural isomers of each other, and they've got different boiling points, and we need to explain why. The question had 5 possible points that you could make, but you only actually needed 4 of them to get the full 4 marks of this question. So you might find, if you compared your answer to someone else's, that actually you've got some small differences and you both got 4 marks. That's perfectly fine for this. So, first off, the comparison we need to start off with is actually between these two versus this one on the right just here. You didn't need to name these as part of the exam question. You could just describe them using the structural formula at the top of each column. But I did rename them just because if you're preparing for the exam, you should be practicing how to name these structures, and I think that's useful for you. Now, we're comparing, like I said, these two to this structure over here, because these two are going to have hydrogen bonding as their strongest type of intermolecular force, whereas this one's just going to have London forces, although you could describe it as having permanent dipole-dipole. So here, the first 3 marks are all about that. We talk about how the first 2 have both got hydrogen bonding, but the third has only got London forces. We say that hydrogen bonds are stronger than London forces, and therefore more energy is required to break the hydrogen bonds. I think a lot of people assume this final point is implied by saying that the hydrogen bonds are stronger, but the mark schemes will see it as a separate point, so don't forget to talk about strength and energy as separate points when you're doing a bonding question in the exam. Next off then, we need to actually compare the first 2 together because whilst they've both got hydrogen bonding, they're going to have different strengths of London forces because one of them is a straight chain and the other is branched. So, here what we're going to talk about is how the first one is a straight chain with no branches, and that gives it more contact points between molecules. Those are 2 separate points, but unfortunately they only got 1 mark. Next, we need to talk about how what that does, the fact it's got more contact points, causes for those things I mentioned before, stronger London forces. And so the straight chain structure has got more contact points and therefore stronger London forces. Now, if you didn't actually mention anything about energy before, about breaking the hydrogen bonds, there was another opportunity to get the same possible mark as earlier on, which allowed you here to say that the London forces in the first structure are stronger than the London forces in the second. And so this was another opportunity to hit that same mark. What you couldn't do was give yourself 2 marks, one for saying more energy up here and another for saying more energy down there. It was kind of an either or. So a little bit of a tricky one to mark, but to be honest with you, I'd be looking at giving everything I've got on page right now. That is the kind of answer I would deliver because you will never see the mark scheme for your own exam. They only get released a year later. You're never going to look at it. You'll be well into university by then, so you're not going to be concerned about it. I would give a full answer rather than think, oh, I didn't need to give that. You wouldn't know about that. So make sure you give as detailed a response as you think is necessary. Next up, we've got a little bit of maths here, and it's the return of the ideal gas equation. We're being told about an amine at room temperature and pressure, and when it's vaporized, we're being told here that we've got a pressure, we've got a temperature, and as soon as we see them, we've got to think PV equals nRT. And we've also been told, this is a sneaky bit of information, that the amine, whatever it is, amine A, it's got 3 peaks in its carbon-13 NMR spectrum. That means it's got 3 different environments. Right then. Now, actually getting to the molar mass of the amine isn't too difficult. As long as you know the correct units for your ideal gas equation, you can get here to the mole value relatively easily. And so at the top here, don't forget, for volume, it's got to be meters cubed. For pressure, it's got to be pascals. For temperature, it's got to be Kelvin. And then your 8.314, not just 8.31, 8.314 is from your data sheet. This all gives us a molar mass of 87, and then what you've got to do is suggest a structure for the amine down here that would give 3 peaks in its carbon-13 NMR spectrum. That means you're not allowed to suggest the straight chain option for this. It's got to be either a secondary or a tertiary amine, and it's got to give me those different 3 environments. The mark scheme for this has got a range of different things that you could have in the answer for this, but I suppose what I'm here to do is point out that you weren't allowed the straight chains because of this sneaky little bit up here which says it's got to have 3 possible environments. Next up, again, as long as you know condensation polymerization, this one isn't too bad. We're not making a condensation polymer at all. We're making a cyclic structure, but it's the same reaction. We're looking at an amine and a carboxylic acid to make an amide bond just here. So following the instructions of this question, we create this cyclic structure, which I think is fairly easy to see. It's this carbon getting connected to this nitrogen just here, which is what that bond is just there. You actually got a mark for this for just the water. So all you needed was one of these 2 products to get the first mark, and just putting the water alongside a completely chaotic incorrect answer would have still got you a mark. If you got both products and it was balanced correctly, which actually is no balancing just here, then you would have got the second mark as well. This next question is an absolute gift. While it's got a lot going on, it's very straightforward. There's no hidden messages in this. It's all about Module 5 transition elements. Now, if you need a recap of this, there's some videos linked at the top of the screen throughout this question, and if you want to have a look at those and then come back to this, I'd more than recommend that because it might help you with understanding some of the vocab I'm using here and where I've got these diagrams and structures from. But I think this is a really good question for straightforward saying, hey, tell me everything you know about this in a level of response format. Again, if you check out the video description, I'll put a video in there about how you should answer level of response exam questions so that you're going into these with a clear mindset. And one of the things you'll hear me say in that video is subheadings, because they allow you to organize your answer alongside bullet points, little bursts of correct vocab and information to make it easy for the examiner to mark, and it makes sure then that they're able to go through your answer and not miss anything out. First thing here then is it's asked me in the question for various different terms. I've given them all a correct definition or description. Ligand substitution, for example. Not really a definition you often think about, but here if we just describe it as one ligand replacing another, then we can't really go wrong with this. But we've got that written as a separate point because it was a separate bold request in the question. Next off, we were asked about complex ions with different shapes and 3D diagrams. I've gone with some really straightforward ones here. I've gone for the Cu2+ with 6 H2Os, and then I've also got this CuCl4 2- here, which is tetrahedral. Now, side by side, these aren't going to take long to draw. You've probably drawn them hundreds of times in your revision or on flashcards for things, and so I think these are nice, straightforward, not overcomplicating examples that you're able to do quickly, and you'll be able to do really clearly and check again to make sure all your bond connectivity is good. You could have suggested for this tetrahedral one, because it's a different shape, you could have gone with square planar and used cis or trans platin, but I think instinctively you would have gone for tetrahedral because you've probably learnt that shape much earlier down the line in Module 2. The equation, actually, the one I've selected here, shows 2 different shapes being involved. There wasn't any credit in the mark scheme for giving more than one equation. It said at least one equation is shown, and that was for 6 marks for this, so you don't need to give any more than that. Maybe on the day of the paper I would have given one more, but here just having at least this one, which uses the 2 that I've actually drawn up here, gives me a well-balanced answer. Next on, we're moving to question 3 here, which is the enthalpy topic, mixed with a bit of organic chemistry. And we can see that propane is being used as camping gas, and the student is trying to determine the enthalpy change of propane by using 2 different methods. So we've got a diagram here. I suppose the big difference is we're used to seeing a spirit burner at the bottom. But as far as diagrams go, it's really clear we're looking at a calorimeter. And when we look at the results table as well, it's very clear here that we're using these top 2 values for the mass of the propane burner before and after to get the mass of propane that was used. And we've got our delta T from the initial and the maximum temperature reached. So it's really obvious what we need to do with this data as well. I think the first part of this, again, nice and straightforward, give good, clear working out for it, but it's Q equals MC delta T. Then what we need to do is negative Q divided by N just here. And we're going to use the mass of propane burnt, which is going to be the difference between these 2 numbers here at the top in order to get the mass value for the propane, divide by 44, which is propane's molar mass, giving us this mole value. And then this negative Q over N gives me the enthalpy change for the combustion of propane, which is negative 1,860 to 3 significant figures, as instructed by the question. Moving on, the student finds that the experimental enthalpy change is much less exothermic than the accurate standard enthalpy change in databases. One reason could be that the student's experiment had not been carried out under standard conditions. That's actually one of the 3, the other 2 are in the blue here, that I recommend you learn as reasons why the data book value for an enthalpy of combustion could be different from an experimental. The other 2, like I said, are shown in the blue. You would say heat loss to the surroundings, which is actually one of the reasons they usually remove as a choice from you. And then the other is incomplete combustion. You were allowed a third one here, which is evaporation of the water, but we've got to be a little bit careful with that because the maximum temperature here wasn't massively high. And so there is a little bit of a gamble associated with that because it, of course, is going to depend on what the maximum temperature reached is in the experiment. So I'd just be a little bit careful with the third one. You don't know how picky they're going to be. This next question is another level of response, and it's using average bond enthalpies to determine the enthalpy change of combustion for propane. Now, you might immediately look at this question and think, well, I can just use the average bond enthalpy values for this reaction equation just here, and surely looking at that equation, that's the enthalpy change of combustion of propane. But actually it isn't. As you can see from the red labels, this, in the enthalpy change of combustion of propane, should be liquid water, and here it's gaseous water. So what's that extra bit of energy that's being used? Well, the question provides us with that information as well. We've got here enthalpy change of vaporization, which, as you can see here, is going from 1 mole of liquid water to 1 mole of gaseous water, and it's an endothermic change. So what we need to do is pair up this enthalpy change, which we're going to find by using the average bond enthalpies, and we need to then use this enthalpy of vaporization to make the enthalpy change that we calculate more like the enthalpy change of combustion for propane. And I'll talk about what the difference between those numbers is going to be and why as I take you through the question. The question itself, if we just want to have a look on the next page at what it's describing, it wants us to determine that enthalpy change of combustion of propane. But I've put my answer all in this section here that I definitely wouldn't recommend you do in the exam, just because then I'm going to have to do less jumping around the paper to show you how I'm using the data. Now, first off, really straightforward beginning. I'm going to use the average bond enthalpies to determine the enthalpy change for this reaction just here. So that's just module 3. I've not shown all my working out for this, but you would really take your way through the molecules nice and carefully, check your data against mine just here if you've made a small mistake, and show your full working out on the day of the exam. Now, this enthalpy change that we've got here is not exothermic enough. So I'll just emphasize that. That enthalpy change that we've got is not exothermic enough to be the enthalpy change of combustion for propane. So how do I know that? Well, just here in that reaction equation, I'm making 4 moles of gaseous water. And what we're learning here in this section for enthalpy change of vaporization is that energy is required in order to go from liquid to gas, which we knew anyway, because that's evaporation, isn't it? So what that means is this reaction is holding on to energy here in this gaseous water. If we were to condense that and get it back to liquid water, we're going to be kicking out this energy. But obviously we're going to be looking at a multiple of that because we've got a nice 4 here in front of the H2O. So let me explain that here with these bullet points. And I wouldn't necessarily include these bullet points in my exam answer. I'm just here using this to describe what's going on. I'm going to need 4 lots of the enthalpy change of vaporization. And that's because the enthalpy change that I've just calculated using bonds broken minus bonds made is less exothermic than the enthalpy change of combustion. And that's because the formation of gaseous H2O requires additional energy equal to 4 lots of the enthalpy change of vaporization included in the question. Whereas the formation of liquid water is going to release more energy to the surroundings, so the enthalpy change is more exothermic for the enthalpy change of combustion of propane. So what I need to do here with my calculation is I need to take this number that I've calculated using bonds broken minus bonds made, and I need to make it more exothermic because I want that gaseous H2O to effectively, theoretically condense and kick out the energy that it's currently got to be part of that gas state. And so what I'm going to do with my calculation is I'm going to do a subtract 4 lots of the enthalpy change of vaporization and look at how much more exothermic my answer is. I get negative 2,217 here. There's a lot going on here actually for a level of response question, and most of the marks are for showing the process nice and carefully. A lot of the marks were for this bit here. You can't skip it. You've got to show them what you've done. They're looking for, have you subtracted or have you added? How many multiples of the vaporization did you use? What sign did you give your answer at the end? These are all things they're looking for. So have a look at the mark scheme. Do not underestimate how much information you had to include here. You'll be surprised by how much you needed to deliver. Moving on here with question 4, and a student is carrying out an investigation to identify 2 different metals, M and X, by 2 different methods. First off, we're going to be analysing the identity of metal M, and the student has said that they're going to be using a back titration technique. Now, there's quite a lot of parts to this, so what I'm going to do is, before we go through the full part of the question, looking at the redox reactions and the stuff about how we know the reaction is finished, I'm going to talk about what the back titration method looks like here and how we're going to use this in the calculation a little bit further in the question, because I think it helps you visualise what's going on. So here, the student has a 100 centimetre cubed sample of 2.10 mole per decimetre cubed HCl, and they add to that 6.9 grams of the metal. Now, that amount of HCl that was being used was a deliberate excess, so they're not going to use all of the moles in the 100 centimetres cubed of HCl. How much of it doesn't react is then analysed in a subsequent titration. So I'll just explain again what's going on here. We've got 6.9 grams of metal M being added to a 100 centimetre cubed solution of HCl. Not all of the moles of HCl react. What we do then is we take the amount of HCl that didn't react and we dilute it with enough deionized water to make a 250 centimetre cubed solution of HCl in stage 2. Then in stage 3, 25 centimetre cubed samples from that diluted 250 solution are titrated against sodium hydroxide. What we're then going to do is figure out the average titer of the sodium hydroxide. We're going to figure out the moles of sodium hydroxide per titration, use the ratio between sodium hydroxide and HCl, which is 1:1, to figure out the number of moles of HCl in a 25 centimetre cubed portion, scale that up to determine how many moles of HCl were in the 250 diluted solution, and that's going to be equal to the number of moles that didn't react with metal M at the start of this process. What we'll then be able to do is use the total moles of HCl that were being used at the start, subtract from that the moles of HCl that didn't react to determine the number of moles of HCl that did react with the unknown metal M. Finally then, we'll be able to use the ratio between those two, that's the moles of HCl that did react, to determine the number of moles of M that were in the 6.9 gram sample, and then we can use the mass value and the moles of M to figure out its molar mass, the AR value for the metal, and the identity of the metal from the periodic table. So let's have a look at the rest of the question, which builds up to this calculation, and see where the links are to our specification. In this first part here, we've got a link to Module 3, the Group 2 chemistry topic, and we've also got a little bit here of Module 5 redox. We've just got to write the overall equation for the reaction of the metal with hydrochloric acid, and then the two half equations. I don't think these are particularly complicated. You're only really going to struggle here if you haven't revised the Group 2 metal topic in a lot of detail from Module 3. Next up, in stage 1, suggest two observations that would confirm all of metal M as reacted. Well, the effervescence or the bubbling stops, and the metal will disappear or will dissolve, you can say as well. In stage 3, write the ionic equation for the reaction taking place in the titration. Well, it's a neutralization, so that's going to be H plus and OH minus gives H2O. And here we go. It's time for the big calculation. So for the big calculation here, we're going to kick off, like I said, with the average titer of sodium hydroxide used in stage 3. We can then use the average titer along with the concentration of the sodium hydroxide to find the moles of sodium hydroxide per titration. There's a 1-to-1 ratio between the HCl and the sodium hydroxide when they react, so that tells me I've got 8.72 times 10 to the power of negative 3 mol of HCl for every 25 centimeters cubed used in the titration. Now remember that 25 centimeter cubed sample used in the titration, that's of HCl, came from a 250 centimeter cubed solution. So if I want to know the number of moles in 250 centimeters cubed, all I need to do is take this mole value and multiply it by 10. And so here, this mole value that I've got is the number of moles of HCl that are in that diluted solution, which are the number of moles of HCl that didn't react with the metal at the very start of this process in step 1. Now, aside from that data, what I also need to calculate is the number of moles of HCl in the original sample before it was added to the metal. So that's 100 centimeters cubed, and it was a 2.10 mole per decimeter cube concentration. The number of moles originally then of HCl is 0.210 mol. What we do now is the gritty bit. We've got the number of moles of HCl in the original solution. We've got the number of moles of HCl that didn't react, and that allows us to calculate here the number of moles of HCl that did react with the metal in stage 1. We are told, and we figured out as well with the reaction equation in the first part of our answer, that the ratio between the metal and HCl is 1 to 2. So what that means is, if I know the number of moles of HCl that reacted with the metal, if I was to half that value, that gives me the number of moles of the metal M that were involved in that reaction in stage 1. I can now do mass divided by moles, and it tells me that my metal is going to be something with a molar mass of 112.4, and that's cadmium. Moving on here with part B, and we're going to be looking at the other metal the student is trying to identify. This time, the student is provided with the carbonate of the unknown metal, and it's got the formula X2CO3. The student measures the mass loss when the carbonate is added to an excess of hydrochloric acid, and here's the equation below. So the reason that there's going to be a mass loss over the course of this reaction equation is because there's a gas released here of CO2. And so the mass that gets lost over the course of the reaction equation is going to be CO2 that's kicked out in the reaction. It's carried out using this method. 100 centimeters cubed of HCl is added to a conical flask and it's weighed. We then add the X2CO3 to the conical flask and it's immediately reweighed, which is going to be tricky to do because they're going to start reacting pretty quickly. After 5 minutes, we reweigh the conical flask and its contents. And that gives us the data just here. What they don't do is tell us how to use this data. We need to interpret that over the course of the question. For example here, we're told to calculate the amount in mol of CO2 released in the reaction. Remember, that's what I said would be responsible for the mass loss. So here, the way that we find the mass of CO2 to begin with, which is actually 2.75 grams, is the difference between these two numbers. The mass before reaction and the mass after 5 minutes. The only difference there is going to be that some CO2 was kicked out by the reaction, and so the difference between those two numbers, which is 2.75 grams, is going to be the mass of CO2 that was released. But we need to convert that into moles, and so that's going to be mass divided by molar mass, 2.75 divided by 44, and that gives me 0.0625 mol. I think this is actually quite tricky for 1 mark, but there are other gifts in the paper, so it's not too bad. Next up, we need to calculate the molar mass of X2CO3 and identify metal X. Using the reaction equation, we can see that the ratio between the CO2 and the X2CO3 is 1:1. And so the X2CO3 moles being used in the reaction are equal to 0.0625 mol. Now, the mass of the X2CO3 is found by using the data in the question, and it's the difference between those two numbers. If we just have a look at what that is, so that's the difference between the reaction when we had both reagents in there at the start and then just the HCl in the conical flask. So the difference here is these two. So the difference between these two numbers here is going to be the mass of the X2CO3. And that's 14.57 grams. So if I want to figure out what the molar mass of the X2CO3 is, because that's going to be how I identify what the metal is by looking at molar mass, I'm going to do the mass that we had divided by the moles, and that gives me 233.12 grams per mole. What I can then do from that molar mass is subtract the CO3 bit, leaving me with just X2. So if I subtract the CO3 bit, that gives me 173.12. If I then divide that by 2, then I've got the molar mass, or we can call it the AR value, of our metal X, which comes out as 86.56. That correlates, not perfectly, but it correlates to rubidium on the periodic table. Sometimes there are slight differences from the value on the periodic table because they may use real experimental data, which is going to have minor differences in, because that happens in practical chemistry. Moving on to part C, we're asked how could we modify the experimental procedure to be confident that the reaction was complete, and in the context of this reaction, we would reweigh to a constant mass. The student finds out that carbon dioxide is slightly soluble in water. State and explain how the solubility of CO2 would affect the calculated molar mass value of the X2CO3. That's quite long-winded, isn't it? So here, I've given you a little bit more information than perhaps I would actually give on the day of the exam, and it's certainly more information that was in the mark scheme, but I really want to explain how I've got to this answer. The mass loss recorded if this happened, so if the CO2 dissolved into the water, which it can do, the mass loss recorded would actually be smaller than it should be. So we should actually be recording more CO2 was being kicked out into the surroundings, but some of it wasn't being kicked out because it was dissolving into the solution. This means that the calculated value of moles of CO2, and then, because we used the ratio, the moles of X2CO3 were smaller than they should be. This causes the MR equals mass divided by moles calculation to give a greater MR value than it's meant to. And there's your answer to the question. If you check the mark scheme, you can see the minimum thing they wanted you to write, but I don't believe without this explanation you may be able to follow exactly what's going on, so hopefully that helps to shed some light on things. Let's take a look here at question 5, and at first glance this question can seem incredibly intimidating, but actually it's very similar to the Arrhenius equation work that you do in module 5, and hopefully the way that I've boxed up the different components of this equation here help you draw those comparisons. Remember, we also do the same kind of thing with the delta G equation, and if you check the video description or the links at the top now, I'll put the Arrhenius equation work there and also the delta G stuff for the equation for a straight line, so that you can see how all of this crosses over and how you could revise ahead of this kind of question. First off here, we need to complete the data table. Please match the pre-existing precision of the data table. Whenever you've got to do this in the exam, please don't throw these marks away. You've got to make sure you match the pre-existing precision in the table and check your numbers in your calculator twice. You will have time to do that if you are nice and methodical with the way you're doing stuff. I would err on the side of caution. Even though the mark scheme showed the bottom row here to the nearest whole number, I would actually give everything I'm putting in here to 3 significant figures, because that looks nice and consistent. They did accept this data at the bottom just here to 3 significant figures with these little decimal places, because I don't believe it's obvious that it's meant to be to the nearest whole number all the way through this bottom row. Next up for part B, state and explain how increasing the temperature affects the position of this equilibrium and whether the forwards reaction is exothermic or endothermic. Right, have a look at this data in the top 2 rows. Now, as you can see here, as temperature increases, the Kp value is decreasing. Now, whenever you increase temperature, you're going to shift the position of equilibrium in the endothermic direction. Remember that. Also, when Kp is getting lower, that means the position of equilibrium is shifting to the left-hand side. Let's pair those bits of information together. As temperature increases, Kp is decreasing, meaning that equilibrium is shifting left, which leads us to our answer. Equilibrium has shifted to the left as temperature increases, meaning that the forwards reaction must be exothermic, because we're only going to shift in the endothermic direction when temperature goes up, and the Kp data is suggesting that the equilibrium is shifting to the left-hand side. That means the forwards reaction is exothermic. Next up here, we've got part C. Now for part C, we need to plot a graph of ln of Kp against 1 over T using the axes provided on the opposite page. This is very similar to the Arrhenius equation work, and it's our way of finding the activation energy that this really compares to the most. Because if we look up here at the equation, we're being asked to find the enthalpy change, and you can see that's inside the gradient term just here. And that's very similar, the same in fact, to how the activation energy is found when we do this kind of thing for the Arrhenius equation work. So what we're going to need to do is find the gradient of the straight line from this, and we're going to then multiply it by the gas constant R, and that's going to give us the enthalpy change here, but what is the activation energy when we do the same kind of thing for Arrhenius in Module 5. So, if we have a look at the data I've got here, I've used my graph to get this data, and the reason I've done that and not just used the data table is because we are explicitly told by the question to use your graph. The marks here are not just, oh, give them 4 if they've got this on the line. You're going to get marks if you have this value in a certain boundary, shown in the blue brackets just there, and you've used data from your actual graph, and your graph, of course, has got to be plotted correctly. So let's have a look at the graph that I've done on the next page. I did find this a little tricky to plot. And of course, you do need to make sure that you've got a gradient that falls inside the boundary that I showed you on the previous page. Now, if you've already plotted your points and you've done your line of best fit, and you want to see what my line of best fit would look like on your graph, here's what I recommend you do. Draw a straight line between the points I'm labeling up here. So at the top here, we're looking for 140, and it's that's the y-axis reading, so right at the very top. And we've got 2.60 times 10 to the power of -3. And then right down here at the bottom, we're at the 40 point, obviously on the y-axis, that's right at the bottom here, and we've got 0.90 times 10 to the power of -3. Please don't tell your maths department about my use of standard form just there. I'm just sticking to the scale on the graph, okay? Now, if you draw your line crossing through those points, you'll have the same line of best fit that I drew, and then you'll be able to compare yours to mine, and then if yours falls outside the boundary, you can see how mine was different and how you may need to tweak how you draw that for your own exam. So, using that, and you can see I've drawn on my triangle in red just here, obviously black ink in your exam, please. but I've drawn that on just here. This is the triangle I'm going to use. As big a triangle as you can do, please. The examiner's report always says that mistakes are made with small triangles. Here I've put my data into the table, change in y divided by change in x, final minus initial each time. Your physics department would be proud. And it gives me a value here for the gradient of 58,823. Now, that's inside the range, it's almost slap bang in the middle here, of the 57,000 to 63,000 that you are allowed on the day of the exam. And actually, very small changes to the gradient of the line can actually take you outside of that range, so please be careful. The reason they've given you a range like this is because they've already done the axes for you, so everyone nationally using the same points and the same axes should fall into a relatively similar boundary. Now, the value here you get of the gradient, m, the value at the moment, which is equal to delta H divided by R, is actually currently in joules. And what we need to do is multiply by the gas constant and divide by 1,000 to get it in kilojoules per mole. Now, what other information do we have that helps us understand that's what we've got at the moment? At the very top of the question up here, we're told that in this equation, enthalpy change is actually joules per mole, which is very unusual. We are always familiar to using kilojoules per mole for enthalpy change. So it is unusual in here that we've got joules per mole. And the gas constant R is joules per mole as well. So what that means is we're assuming our gradient then is going to still be in that joules territory here. So what we need to do to get to a kilojoules per mole answer, we need to divide the gradient by 1,000, just like we would do for the activation energy in the Arrhenius equation work, I'd just like to say, and then multiply by R in order to get the enthalpy change in kilojoules per mole, which is negative 489. Next bit. Explain how delta S could be calculated from a graph of ln of Kp against 1 over T. So what we would now do is, in order to find delta S, we consult our equation at the top just up here, and it's a little bit different from the Arrhenius equation work, but it's still going to be using the intercept of the y-axis. It's just we're used to seeing exponentials if we're doing the Arrhenius equation work here, but we've got another presence of R, two presences of R in this equation. And so what we need to do is use the y-axis intercept for 1 mark, and then delta S equals R times the y-axis intercept to get the other. And we're allowed to do that because our x-axis goes right back to 0 here, so we can use that intercept of the line. The mark scheme does allow you to say, instead of use the y-axis intercept, you could talk about extrapolating your line to the y-axis intercept if you want to go into that much detail. This question is about two different types of acid found in organic compounds, carboxylic acids and sulfonic acids. Sulfonic acids, not in your A-level, so there's going to be a bit of application towards them. Here, though, I think a straightforward start, if I'm honest. We've got here some bond angles and names of shapes, which is linking Module 2 to organic chemistry. You should be able to predict the bond angles in a lot of organic compounds, especially all of those you encounter at A-level. And this carboxylic acid one is the same bond angle that we would expect to see in aldehydes, ketones, alkenes, benzene, and obviously the carboxylic acid here, but also acyl chlorides, amides, esters. This is a really common angle and shape you need to be aware of. The sulfonic acid one is that we would see in alcohols, carboxylic acids as well, and it's the one surrounding that oxygen. When it's in two covalent bonds, it's still got its two lone pairs, making it 104.5 degrees and nonlinear. Tricky question now, using acids, bases and buffers alongside organic chemistry. Ethanoic acid and methane sulfonic acid are both monobasic acids. The pKa values are shown in the table. That's a really negative pKa there for the methane sulfonic acid. A student suggests that 1 mole per decimeter cubed sulfonic acid should have a lower pH than 1 mole per decimeter cubed ethanoic acid. I mean, the student's right, but we'll explain why. Write an equation showing conjugate acid-base pairs for the equilibrium of sulfonic acid with water, not with the ethanoic acid, with water, and explain with reasons whether the student is correct about the sulfonic acid having a lower pH when it's got the same concentration as ethanoic. I think this is really clumsy. Not to be critical, but I think it's clumsy in the sequence it asks you to do things, and actually here this would take a couple of read-throughs to make sure you're doing the right stuff. So first off, I've got my acid-base pairs just here, which are labelled up. Sulfonic acid added to water. If you want a little brush up on the acid-base pair stuff, I'll put a video in the video description for you, and I'll link it at the top now, so you can click on that and have a look at acid-base pair work if you want. Now, furthermore, the student is correct, like I said before. And the reason we know that is because the sulfonic acid has got a lower pKa value, which means it would actually have a bigger Ka value. And that means it dissociates more than the ethanoic acid. And so it's going to have a more acidic solution. For this final section of the question, we're having to predict some curly arrows. And I'm not trying to cut this video short, but I've actually already done a tutorial for this exact exam question where I go into loads of detail about how we predict these curly arrows, along with a follow-up video on another set of predicting curly arrows in organic chemistry. So what I'm going to do is, at this point, thank you for watching the video so carefully and for going through it with me, and follow the link to watch the next video here, which is all about this exam question and predicting curly arrow movement. Thank you very much again for watching. Please leave this video a like before you go, and until next time, happy revising.